Welcome back to the deep dive. In the tech world, we are constantly, and I mean constantly, obsessed with the shiny and new.
Oh, absolutely. It's always the next big thing.
We talk about the latest AI models, the newest JavaScript frameworks that seem to pop up every Tuesday, and quantum computing. But
AI is different.
today we are doing something completely different. We are grabbing a shovel and we are digging down, way down through all those layers of abstraction and sediment to hit the absolute bedrock of modern computing.
The foundation, the concrete slab that holds the entire skyscraper up.
We're talking about C. And I feel like for a lot of people, C has this almost mythical reputation. It's spoken about with this mix of reverence and, let's be honest, a little bit of fear.
A healthy amount of fear, maybe.
Right. It's described as the language that gives you the keys to the kingdom, but it also, removes every single safety rail.
That is a very, very fair assessment. C is where the rubber meets the road. It is where software shakes hands with hardware. It doesn't hide anything from you. It forces you to understand what the machine is actually doing with its electrons. It's not about magic. It's about mechanics.
And to guide us through this mechanic shop, we're relying on a massive, really comprehensive set of source materials authored by Dr. Gandhi Bilanka.
A fantastic resource.
Specifically, we're looking at Dr. Gandhi Bhaskar Petrudelanka's work, C Programming Basic to Advanced. And when I say comprehensive, I mean Dr. Lanka takes no prisoners. He starts from absolute zero.
Not a thing assumed.
And goes all the way to memory manipulation, pointers, all the scary stuff.
It really is a roadmap. Dr. Lanka's work is just fantastic because he doesn't just throw syntax at you. He builds the logic of how a computer actually thinks. He frames C not just as a tool you use, but as a mindset you adopt.
So here is our mission for this deep dive. We are going to simulate the journey of a complete novice. We're going to pretend we have never written a line of code in our lives.
Blank slate.
Total blank slate. We are going to set up the environment, write that first iconic hello world, and then we are going to push all the way into the deep end pointers, structures, file handling. We want to answer the question, why is this language from the 1970s still the gold standard for understanding how computers work?
It's a journey from I hope this works to I control the memory of this machine.
I love that. So let's crack the code. Why C? Why now? Why are we looking at Dr. Lanka's notes in an era of AI coding assistants that can write code for you?
Because C is the truth. I mean, when you learn Python or Java, there are layers and layers of abstraction between you and the processor. The language handles memory for you. It handles data types loosely. C just. It strips all that away.
It's just you and the metal.
Pretty much. Learning C teaches you about memory addresses, about how data is physically stored in the silicon chips. If you master C, you understand computing on a fundamental level.
It's like learning to drive a stick shift before you ever drive an automatic. Once you understand the gears and the clutch, you really understand the car.
Precisely. And once you can drive stick, you can drive anything.
All right, let's get our hands dirty. Segment 1, the environment and the hello moment. Dr. Lanka calls this the setup. If I decide right now I want to write C, I can't just open Microsoft Word and start typing, right? That's not how it works.
Definitely not. No, you need a specific toolkit. We can call them the three musketeers of C development as the source material lays them out.
Okay.
First, you need a place to write the code. That's your code editor. Dr. Lanka explicitly suggests VS Code, Visual Studio Code.
Which is pretty much the industry standard right now for everything, it feels like.
It is, and for good reason. It's lightweight, it's colorful, its syntax highlights your code so you can spot errors. It's just a great place to work. Think of it as your workbench.
Okay, workbench, got it.
But having a workbench doesn't build the engine. That brings us to the second musketeer, the compiler.
This is the translator, right? The thing that turns my English-like C code into something the computer can actually understand.
Exactly. A computer does not understand C. It doesn't understand if, while, or print. It only understands machine code raw binary ones and zeros. The compiler takes your human-readable C code, that hello.c file, and transmutes it into an executable file the machine can actually run.
And Dr. Lanka notes that this changes depending on your operating system. It's not one size fits all.
It does. It's platform specific. If you are on Linux or a Mac, you are likely using GCC, the GNU compiler collection. It's legendary. It's been around forever.
Right.
If you are on Windows, Dr. Lanka points you toward MinGibU, which is essentially a port of GCC for Windows. It gives you that same power in the Windows environment.
Okay, so that's two. We have the editor, the workbench, we have the compiler, the master craftsman who builds the thing. What's the third?
The third is the one that trips everyone up.
Oh, I think I know what you're talking about.
Yeah.
I remember tripping over this back in the day. The path, I recall seeing this in the notes, path environment variable. What is that and why does it matter so much?
This is a rite of passage for every new programmer. I promise you, everyone has fought this battle.
The command not found error? I remember it well.
Exactly that. So imagine you are in your command line, the terminal. You type GCC to run the compiler. The computer acts like a clerk in a massive library. It has to go find the program, the book, called GCC. It doesn't magically know which shelf or which folder on your hard drive it's stored in.
It's not omniscient. It doesn't just know where you installed things.
Far from it. The path is basically an address book you give to that clerk. You are telling the operating system, hey, when I type a command, look in these specific folders to find the program. You have to manually add the folder containing your compiler, usually the bin folder inside MinGW, to this path variable.
So if I don't do that, I type GCC, and the computer just says, command not found. It shrugs its shoulders.
Exactly. It stares at you blankly. It's like you asked the librarian for a book but didn't tell them which section of the library to look in. Setting the path ensures that no matter what folder you are working in, the terminal can find your compiler tools.
Okay, so we have the editor, our workbench, the compiler, our tool, and the path, which is the map to find the tool. And you get to the workflow. The rhythm of CPA. Dr. Lanka says it's a two-step dance, isn't it?
It is. It's very deliberate. Compile, then run. It's distinct from, say, Python or JavaScript, where you just sort of hit play.
So I've written my first file, hello.c. What's step one?
Step one is compiling. In your terminal, you navigate to the folder where you saved your file, and you type gcc hello.c. The compiler wakes up, reads hello.c, checks it for errors, missing, semicolons, typos, that kind of thing. And if it's clean, it spits out a brand new file.
And that new file is the program, the executable.
Right. On Linux or a Mac, it defaults to a file named .out.
Does a .out stand for anything? It's such a weird name.
It's a relic. Historically, it stood for assembler output. It's a carryover from the old Unix days. It's kind of charming in a nerdy way.
So how do I run it? I just type in a.out.
Almost. You have to type .a out. The / tells the terminal to look for the file in the current directory.
Another one of those little details.
Always the details. On Windows, it's a bit more straightforward. The compiler usually creates a.exe, and you can just run it by typing a.exe.
That distinction, compile time versus runtime, is huge, isn't it? It means there are two different stages where things can go wrong.
Exactly. You catch syntax errors, your typos during compilation. The compiler will refuse to build the program if you forgot a semicolon, but you catch logic errors like you told it to add when you meant to subtract during the run. That's when your program runs but does the wrong thing.
Got it. Okay, let's dissect that first program, the classic Hello World. Dr. Lanka breaks down the anatomy of this minimal program. It seems so simple, but every single line is doing some heavy lifting.
It's deceptively dense.
It starts with hashtag include stdio.h. That looks cryptic.
It does, but let's unpack it. The hashtag means it's a command for the preprocessor, a tool that runs even before the compiler. Include is the command, and stdio.h is the file you're including.
So what's in that file?
Stdio stands for standard input-output, and the .h means it's a header file. Think of it as a toolbox.
A toolbox. I like that.
It's the perfect analogy. C is a very small, stripped-down language. It doesn't inherently know how to talk to your screen or listen to your keyboard. It needs a library of functions to do that. ncdo.h is the toolbox that contains the instructions for functions like print. Without that line, you can type print all you want, but the compiler will just say, I don't know what that word means.
So we grab the toolbox first. Then we see int main.
The entry point. This is non-negotiable. Every single C program in existence must have a function named main. When you run your executable, the operating system looks for a function specifically named main and starts running the code from there.
Okay, so that's where the story begins, and then we have the curly braces.
The scope.
Yeah.
The braces define the beginning and the end of the function's body. Everything inside those braces belongs to main. It's the container for your code.
And inside, the famous line, print. Hello, world men. We'll get back to the details of print it, but I want to jump to the end. Return 0. Why are we returning 0? Who are we returning it to?
We are returning it to the operating system. See how the function starts with int main. That int at the start is a promise. It's promising the OS that when it's done, it will return an integer value.
A status code.
Exactly. By convention, returning 0 signals success. It tells the OS, I finished what I was doing and nothing blew up. If your program ran into an error, you might return 1 or -1 or some other number to signal a specific problem. It's a way for programs to communicate their outcome.
Before we move on, I noticed something in the source material about casing. Dr. Lanka really emphasizes this. Main with a capital M is not the same as main with a lowercase m.
Correct. And this is a common stumbling block for beginners coming from other languages.
Mhm.
C is strictly, brutally case sensitive.
So if I accidentally type int instead of int,
The compiler will throw an error. It has no idea what int is.
Huh?
In C, age, and AGE are 3 completely different and unrelated variable names. The compiler will not guess what you meant. It demands precision.
it's strict. I like that. It forces discipline from the very beginning.
It absolutely does.
Okay, we've got hello world on the screen. The foundation is laid. Now let's move to segment 2. We need to actually do something with data. This brings us to variables and data types. Dr. Lanka defines a variable as a named memory location.
Right, and that's the key. Think of the computer's memory, the RAM, as a massive warehouse full of millions and millions of tiny, unlabeled boxes. A variable is simply us walking up to one of those boxes, claiming it, and slapping a label on it so we can find it again later.
And we have rules for those labels, the variable names.
We do. Dr. Lanka outlines the syntax rules clearly. The name must start with an alphabet or an underscore. You cannot start a variable name with a number.
So one player is illegal, but player 1 is fine.
Exactly. Also, no spaces. If you want a 2-word name, you use an underscore, like final price, or you use camel case, like total marks. And no special symbols like @ or hashtag or @.
And no keywords, right? I can't name my variable int or return.
Correct. Those words are reserved for the language itself. They have a special meaning to the compiler, so you can't use them as labels for your memory boxes.
The notes also mention good practice. This isn't just about what is allowed by the compiler, but what is smart for the human programmer. Dr. Lanka suggests meaningful names.
This is so important. It's about readability and maintainability. You might write a piece of code once, but you or someone else will have to read it 10, maybe 100 times.
So A equal BC is legal, but terrible.
It's terrible because if you come back to your code 6 months later, you have no idea what that means. But if you see total price, unit price quantity, it's completely self-explanatory. The code documents itself.
Now, in that warehouse of memory, not all boxes are the same size. This is where data types come in. The source emphasizes what it calls the big 3: int, float, and char.
These are the fundamental primitives. Int is for integers, whole numbers. -1, 0, 42, no decimals allowed. If you try to store 3.14 in an int variable, the 0.14 just gets truncated, chopped off. You're left with just 3.
Okay, so int is for counting things. What about float?
Float is for floating point numbers. That's the technical term for numbers with decimals. 3.14, no 0.02, 2.5. Think of it for measurements, prices, scientific calculations.
And char. That sounds like character.
It is. It holds a single character, not a word, not a sentence, just one letter, number, or symbol, like A or dollar or 7.
And this choice of data type connects back to memory size.
Yeah.
One of the things that makes C special, according to the source, is this thing called the size of operator. You can actually ask the computer, how much space does this box take up?
Yes, this is a very C thing to do. In a lot of modern languages, you just don't think about this. In C, it's encouraged. You can write a line like print size is size 10, and it will tell you how many bytes of memory an integer uses on your specific machine.
And the results can vary.
They can, depending on the system architecture, but typically, on modern systems, an int takes 4 bytes. A float also usually takes 4 bytes. And a char is tiny. It takes just 1 byte.
Why does a learner need to know that? Why not just let the computer handle it? Why does Dr. Lanka emphasize this?
Because in C, memory is a finite resource that you are responsible for managing. If you are programming a microcontroller for a washing machine or a smart thermostat, you might only have a few kilobytes of RAM to work with, total.
Wow.
Knowing that an int takes 4 bytes and a char takes 1 byte helps you make efficient choices. You don't use a dump truck to carry a single letter. You pick the right size tool for the job to avoid wasting precious space.
That makes perfect sense. It's about efficiency and understanding the constraints of the hardware.
Exactly.
Before we move on from data, we should touch on constants and comments. Constants seem straightforward. They're just values that don't change.
Right. The number 3.14 is a real constant. The number 42 is an integer constant. And the letter A, and notice in C, single characters are strictly enclosed in single quotes, is a character constant.
Single quotes for char, double quotes for strings, like in print,
A crucial distinction, yes.
and comments. The notes say they are, for humans, ignored by the compiler. They seem optional. Are they important?
They are vital. They are one of the most important parts of writing good code. You have single-line comments that start with and go to the end of the line, and you have multi-line comments that start with and end with.
And what's their purpose?
To explain the why, not the what. The code tells you what it's doing. A comment should explain why you chose to do it that way. The compiler deletes them completely before creating the executable, so they have zero impact on performance. They are purely notes for yourself and for other people who will read your code.
Okay, let's get conversational with the computer. Segment 3, input and output. We've seen printf a little bit, but let's go deeper. Speaking out.
Right, so we mentioned print is in the studio.h library. The F in print stands for formatted, and that's the key. You aren't just dumping raw text to the screen, you are carefully formatting it using placeholders.
And that involves these things called format specifiers, the source list, %, %. What are those?
Imagine print as a sentence with holes in it that you need to fill. You want to print, my age is 25. You could write print, my age is 25. But what if the age is stored in a variable?
Ah, so you need a placeholder.
Exactly. You write print, my age is %age. The % is the placeholder, the hole, for a decimal integer. Print sees the %, looks at the next argument, age, and plugs its value into that hole.
And % is for floats, and % is for chars.
Correct.
That.
Print, the price is % cost. Print, your grade is % letter grade. It lets you mix static text with dynamic variable data seamlessly.
And the source emphasizes something else here. Escape sequences, specifically N.
The new line character. This is so important for making your output readable. If you write 2 print statements without an N,
You just mash together on one line.
they just run on right into each other. It looks like a mess. Adding N at the end of your string is like hitting the Enter key on your keyboard. It moves the cursor down to the start of the next line, keeping your output neat and tidy.
Now for the other side of the conversation. Listening in, scanf. This is how we get user input. And this is where we encounter the first really, truly mysterious symbol in C, the ampersand.
Ah, yes. The address of operator. This is the first big conceptual hurdle.
The code, according to Dr. Lanka, looks like this. Scanf. Capersand, pepper age. We didn't use it in print. It feels so random.
It's not random, but it requires a mental shift. Think about the difference between reading information and delivering a package. When you use printed, you are telling the computer, go to the memorial box labeled age, look inside, make a copy of the value you find, and show me that copy on the screen. You just need the value.
Okay, that makes sense.
But when you use Scamp, you are asking the computer to take a value from the keyboard and put it into the box. You are a delivery driver. You can't just yell the name age into the void and hope the package gets there. You need the specific physical address of the house.
So in age isn't the value of age, it's the location of age in memory.
Precisely. The NAGE means the memory address of the variable age. You are giving Scamp the GPS coordinates of the variable, so it knows exactly where to dump the input from the user.
That is a fantastic analogy. So printf is reading the mail, it just needs to know what the letter says. Scanf is delivering the mail, so it absolutely needs the street address.
That's a perfect way to put it. And if you forget the NN Scamp, a very common beginner mistake, your program will likely crash. It will try to write data to some random invalid location in memory, and the operating system will shut it down.
It's powerful, but also a little dangerous.
That's C in a nutshell.
The source material gives a great mini program example here. A simple calculator really ties this all together.
Right. It's the first real interactive program a learner builds. You declare 2 integer variables, say int a(b). You print a message asking the user to enter 2 numbers. Then you use Scamp, procludine presin and b, to read both numbers in.
You can read 2 at once.
You can. Scamp is smart enough to handle that. Then the final step is to print the result. Print F. The sum is per C(d), A plus B. It takes 2 inputs from the world, does a calculation, and gives an answer back. It's a complete conversation.
I love that. And speaking of math, that leads us perfectly into segment 4, the logic engine, operators and flow control.
This is where programs start getting smart. We've got the basics. The standard arithmetic operators plus for addition, for subtraction, for multiplication, and for division.
And one that might be new to some people, the modulus operator.
The modulus operator gives you the remainder of a division. So 10% in 3 isn't 3.33, it's 1, because 3 goes into 10 3 times with 1 left over. It's incredibly useful for things like checking if a number is even or odd. Number percent, too.
We have relational operators. Comparing things.
Greater than I, less than I, greater than or equal to, and so on. The one to watch out for is for checking equality.
Right. A single is assignment, like x before 5, which means put 5 into x. A double, like x equals 5, is a question. It's a value in x equal to 5.
Mixing those up is another classic bug that can be really hard to find because x equals 5 in an if statement is actually valid C code. It just doesn't do what you think it does.
Oof. And then we have logical operators.
And for A and D, for OR, and for NOT, these let you combine conditions. If age 18 and not has license equals 1, both have to be true. If is raining is cold, only one needs to be true.
The source mentions you can combine all of these into long, complex expressions.
You can, but Dr. Lanka wisely notes that readability is key. Just because you can write a massive, complex condition on a single line doesn't mean you should. Sometimes breaking it up is much clearer for the human reading it.
Now let's make some decisions. Conditional statements. The if-else ladder is the first one.
This is the fundamental way a computer makes choices. The grading example from the source is perfect. If marks are greater than or equal to 90, print A. Else if marks are greater than or equal to 75, print B. Else if, and so on, down the ladder.
And it checks them in order, right? Once it finds a true one, it stops.
Exactly. As soon as it finds a condition that is true, it executes that block of code and then jumps completely past the rest of the ladder. It's efficient.
There's another structure for decisions mentioned, the switch case statement. When would you use that instead of if-else?
Switch is great when you are checking a single variable against a list of specific discrete values. The classic example is a menu. Enter 1 for new game, 2 for load game, 3 for options. You switch on the user's choice, case 1, do this, case 2, do that. It can be cleaner than a long chain of if, choice 1, else if, choice 2.
But the source warns of a trap here, a very specific C feature called fall-through.
The fall-through is a huge trap for beginners. In a switch statement, if your code matches, say, case 1, it starts executing the code there. If you do not include the special keyword break at the end of that case,
It just keeps going.
it just keeps on executing the code for case 2 and case 3 and so on until it hits a break or the end of the switch. It falls through the cases.
So it doesn't stop automatically after it finds a match.
No, you have to explicitly tell it to stop. Now, this is technically a feature, not a bug. It allows you to group cases together that should do the same thing, but for beginners, it's almost always a source of bugs. The rule of thumb is end every case with a break.
So always remember your break statements. Now let's talk about repetition. Looping, repeating work. The source lists 3 main types: for, wait while, and do while.
The for loop is your workhorse. It's best when you know in advance the number of times you need to do something. Count from 1 to 10. Process all 50 elements in this array.
The syntax is a little dense for int I1, I10, I++.
It is, but it's powerful. It packs 3 things into one line. The initialization in I1, the condition to continue, and the update after each loop, I++A, which means add 1 to I. It's concise and clean for counter-controlled loops.
And while. When would I use that?
While is for when you don't know how many times you'll need to loop. The repetition depends on a condition being true. Keep asking for a password while the user enters the wrong one. You don't know if that will be 1 time or 20 times.
So for is for counting, while's for waiting for a condition to change.
That's a great way to think about it.
And the third one, do while. This one always seemed a little odd to me. How is it different from while?
It's unique in one very specific way. It checks the condition after the loop body runs, not before. This guarantees that the code inside the loop will run at least once.
Ah, I see. So it's perfect for something like a menu. You have to show the menu options at least 1 time before you can ask the user for their choice and check if it was valid.
Exactly. That's the canonical example. Do showman, get choice, while, choice, and quit.
And within any of these loops, the source mentions 2 control keywords, break and continue. We've seen break and switch.
It does the same thing in a loop. Break is the emergency eject button. It gets you out of the loop entirely immediately. Continue, on the other hand, is the skip button. It stops the current iteration and jumps right back to the top of the loop to start the next one.
Moving on to segment 5. We're building bigger programs now, and we need to stay organized. Functions and arrays.
Yes. As your programs get bigger and more complex, you can't just keep putting everything in main. It becomes a huge, unreadable mess. Functions allow you to break your code down into smaller, logical, reusable blocks.
Dr. Lanka makes a distinction in the material between library functions and user-defined functions.
Right. Library functions are the pre-written ones we borrow from toolboxes like stadio.h printalphys and scamp are library functions. User-defined functions are the ones we write ourselves to solve our specific problems.
And there's a template for writing them. The source says return type function name parameters.
That's the signature. You declare what kind of data it will return, or void if it returns nothing. You give it a name, and you specify what data it needs to do its job, which are the parameters in the parentheses.
And the classic example is an add function.
A perfect example, int add, int A, int B. This function's signature says, I'm named add, I need 2 integers to work, and I promise to give you an integer back. The body would just be return a plus b.
And the why of this is reusability, right?
Reusability, readability, and easier debugging. If you need to add numbers in 10 different places in your program, you just call the add function 10 times.
Yeah.
You don't rewrite the a plus b logic every time. And if you discover your addition logic is wrong, you only have to fix it in one place, inside the function.
Now, arrays. Lists of data. How does C handle these?
An array is a collection of variables of the exact same type that are stored in contiguous memory. That word contiguous is really important in C. It means they are neighbors, sitting right next to each other in RAM, one after the other.
So I can declare an array of 5 integers, like int marks 5.
Yes, and the computer will set aside a block of memory big enough for 5 integers, all in a row.
And the golden rule of arrays in C, the one that gets every beginner.
Zero-based indexing.
If I have an array of 5 marks, the first mark is not at index 1.
Never. It is at marks 0, the second is marks 1, and the last one is at marks 4. The valid indices are 0 through 4.
And if I try to access marks 5,
You are stepping outside the bounds of your array. You're reading or writing to memory you don't own. In the best case, your program crashes. In the worst case, you silently corrupt some other piece of data and create a bug that is incredibly difficult to find.
so you have to be very careful with your loop boundaries.
Very careful. The source shows how to input data into an array using a loop, which is the standard way.
Right. Since an array is just a list, you use a for loop that counts from 0 up to the size of the array. For indice, I05, I++. And inside that loop, you scamp into markc. The loop variable I perfectly steps through the array indices 0, 1, 2, 3, and 4. It automates the data entry process.
Okay, we are getting into the deep water now. Segment 6, the advanced toolset. Strings, pointers, and structures. Let's start with strings. The source says C doesn't technically have a string data type, which seems like a huge omission.
It does seem strange from a modern perspective, but it's part of C's philosophy of not hiding the mechanics. A string in C is just an array of characters, that's all it is. But there is a secret ingredient, a special convention.
The null terminator. The null terminator, the null. It's a special, non-printable character that acts as a sentinel value. If you have the name Gandhi, it's stored in a character array as GANDHI, and then, crucially, the 0 character at the end.
And why is that so important?
Because it's how functions like print know when to stop printing. When you say print sense name, it starts at the beginning of the array and prints characters one by one until it finds that 0.
So without that terminator, the computer would just keep reading memory after the name.
Exactly. It would print Gandhi, followed by whatever random garbage data happens to be sitting in the next memory slots until it randomly hits a byte that happens to be 0 or the program crashes. The null terminator is absolutely essential for C strings to work.
The source also warns about a danger with using scamp to read strings.
A huge danger. Scamp% name is simple to write, but it's very fragile because it stops reading at the first whitespace character. It finds a space, a tab, a new line.
So if I'm asked for my full name and I type John Smith,
Scamp sees the space after John and stops. The name variable will only contain John. Smith gets left behind in the input buffer, waiting to cause problems for your next stamp.
so what's the solution for reading full lines of text?
The recommended solution in the source is a function called flavgets. It stands for file get string, but it can be used for keyboard input too. The call looks like flavgets. Name, psi of name.
That looks more complicated.
It is, but it's much safer for 2 reasons. 1, it reads spaces, so it can handle John Smith. 2, you tell it the maximum size of the array, size of name. This prevents a dangerous bug called a buffer overflow, where a user could type in 1,000 characters and overwrite other parts of your program's memory. Flavgets is just fundamentally safer.
Safety first. Now, the topic everyone dreads, pointers.
The big one, the rite of passage.
I feel like this is where half the computer science students either get it and feel like a god or just hit a wall. Why is this so hard conceptually?
It's hard because it requires you to think about 2 layers of reality at the same time. There is the value of a variable, what is inside the box, and the address of a variable where the box is located in the memory warehouse. Pointers are variables that don't store values like 10 or A. They store addresses.
Okay, so pointer points to another variable.
Exactly. And there are two key symbols. The ampersand NS, which we already saw with scanf, means address of. So NX gives you the memory address of X.
And the other symbol is the asterisk A.
Right. The asterisk is used in two ways. When you declare a pointer, like int p, it means p is a pointer that can hold the address of an integer. But when you use it with an already existing pointer, like p, it means the value at the address that p is pointing to. This is called dereferencing.
So if int x equals 10, and I said int p equals nx, then p holds the address of x, and p is equal to 10.
You've got it. P becomes an alias for x. If you then say p equals 20, you have changed the value of x to 20.
Why? Why do we do this mental gymnastics? What's the point?
Control and efficiency. This is a huge theme in Dr. Lenka's material. Imagine you have a massive data structure, maybe an image file that's 500 megabytes in memory. You want to pass it to a function to rotate it.
Okay.
If you pass the value, the computer has to make a complete copy of all 500 megabytes just for the function to use. That's incredibly slow and wastes a ton of RAM.
But if I pass a pointer to it,
You just pass the address. Hey, the image data starts at this location in memory. An address is tiny, just 4 or 8 bytes. It's instant. The function can then work on the original data directly. This is called call by reference, and it's one of the most powerful uses of pointers.
that makes it click. It's about not having to lug all the furniture around when you can just give someone the key to the house.
That is the perfect analogy. And it also hints at the danger. If you give the key to a badly written function, it might wreck your furniture.
Power and responsibility.
Yeah.
And that brings us to structures.
Structs are how we model complex, real-world objects. Arrays are great, but they can only store multiple values of the same data type.
But a student isn't just a list of integers.
Exactly. A student has a name, which is a character array, an age, which is an int, and a CGPA, which is a float. They're all different types. A struct lets us bundle those different data types together into a new, single, custom type.
So I can define a struct student and then create variables of that type.
Yes. Struct student, student1, and then you access the individual parts, the members, using the dot operator. Student1.age equals 20. Struckypie, student1.name, Gandhi. Student1.cgpa equals 9.5. It organizes related but different data into a clean, logical package.
Okay, our toolset is almost complete. Finally, segment 7. Persistence. Everything we've done so far, all our variables, our structs, it all disappears when we turn off the computer. It's all in volatile RAM. File handling is about saving it to the hard drive.
Moving beyond volatile memory, yes. This is how programs save their state, create log files, or work with large data sets. Dr. Lenka outlines the flow very clearly. First, you need a special kind of pointer, a file pointer.
File EFP.
That's the one. It doesn't point to a variable in memory, it points to a file on your disk.
And you have to open the file before you can use it, with open.
Correct. And when you open it, you have to choose a mode. The source highlights the main three: R for reading from an existing file, W for writing to a file, and A for appending to a file.
What's the difference between writing and appending? They sound similar.
They're very different, and you have to be careful. W for write mode is destructive. If the file doesn't exist, it creates it. If the file does exist, it wipes it completely clean and starts fresh from the beginning.
Oh, so you could accidentally delete all your data.
Easily. A for append mode is safer. If the file exists, it just opens it and puts the cursor at the very end, so anything new you write gets added on without disturbing the old content.
And once the file is open, how do we write to it?
We use functions that look very familiar, fprint and fscanf. They work exactly like print and scanf with format specifiers and everything. The only difference is that their first argument is the file pointer, fp. You're telling the function to send the text to the file instead of to the screen.
So fprint UA, name.percent, age.percent, name age.
Exactly that.
And after we're done writing, what is the most important mandatory step?
Fclose. You must close the file.
Why? What happens if I forget?
Two things. First, for efficiency, the operating system often buffers data. It might hold your written data in a temporary holding area in memory and only write it to the physical disk in chunks. Fclose forces that buffer to be written to be flushed to the disk, ensuring your data is saved.
So if my program crashes before I close, I might lose the last few things I wrote.
You might. The other reason is that it's good practice. It releases the file handle, freeing up operating system resources and allowing other programs to use the file. It's like hanging up the phone when you're done with the call.
So open, write, or read, and then close. The holy trinity of file handling.
Indeed. It's a simple but crucial pattern.
Wow. We have covered a lot of ground. I mean, we really have. We started with the absolute basics of installing a compiler and ended with writing complex structured data to a permanent file on the hard drive.
It is a massive arc. It's the entire journey from a program that just talks to itself to a program that can talk to the user, make decisions, and remember things permanently.
Dr. Lanka's source material really does cover that full spectrum. And I think the key takeaway here, for me at least, is what you said at the very beginning. This isn't just about learning C syntax.
No, not at all. It's about learning the machine. It's about understanding the cost of your code. When you write C, you are manually managing memory. You are thinking about the size of your data types. You are handling the addresses, the pointers. You're in charge of everything.
It builds character. Is that what you're saying?
It builds responsibility. In high-level languages like Python or JavaScript, the language has a garbage collector that cleans up your memory for you. It's easy to be wasteful because the computer cleans up after you.
Mhm.
In C, if you allocate memory and you don't free it, you create a memory leak. You can, over time, crash the entire system.
You have to clean up your own mess.
You have to clean up your own mess. And that teaches you to be a tidy, efficient programmer, no matter what language you use later.
So here's my final thought for you, the listener, to chew on. We live in a world of automated, high-level languages, of AI assistants and garbage collectors. Does learning C in this day and age make you a more responsible, a more complete programmer because you are forced to actually understand the cost and the mechanics of the code you write?
I believe it absolutely does. It changes how you see all code. You stop seeing magic and you start seeing the mechanics, the gears turning underneath. And once you see the mechanics, you can debug anything. You can optimize anything. You can build anything.
That is a powerful place to end. Thank you so much for guiding us through the bedrock of computing.
My pleasure. It was a lot of fun.
And to our listener, go download VS Code, set up your compiler, configure your path, and write that hello world. It's the first step into a much larger, more powerful world. Thanks for listening to this deep dive.
Happy coding!